Hi, welcome to this next video on linear programming duality. Previously, we had been discussing the concept of weak duality in linear programming, and we had illustrated the concept by taking the dual of a particular linear program, and it's this linear program which appears here on the left. And if you recall what happened in that video, what happened is that we weren't able to directly take the dual of this linear program because the constraints came in all sorts of different types. And it wasn't of a uniform format. So what we had to do first is we had to do a conversion to a reformulation of the linear program where all the constraints were of a uniform type. So we had all the matrix constraints were less than or equal to constraints, and all of the variables were free variables. And then from that form of the linear program, we were then able to take the dual of the linear program, which was this linear program here on the right. So that's what happened in that video. Here, I'm actually just going to show you how we can skip that middle conversion step entirely, and we can just jump right to the end, and we can take the dual immediately, regardless of how the initial formulation of the linear program was given. So this will be a faster method in the sense of we're taking the dual directly rather than first doing a conversion to a different format. Okay, and so this is totally general. It will work for any linear program, not just this one in question here. But nonetheless, let's still take the dual of this particular linear program, which appeared in the prior video as well for illustrative purposes. So we took the dual before, and we're going to take the dual again. And the difference is that now we're not going to do the conversion. We're simply going to directly take the dual from the start. So what's the main idea of taking the dual? We want, since this is a maximization problem, the dual is going to be a minimization problem, where it's minimizing an upper bound on this objective primal objective function. So again, in order to construct the upper bound, what we do is we take a linear combination of the matrix constraints. But now the constraints are not all of the same type. And so correspondingly, the dual variables, which are the things that get multiplied by the left and right-hand sides of these constraints here, those dual variables also will not all be of the same type. So what we have to do is we have to consider each component individually. That is, we look at each constraint one at a time, and for each possible, for each case that it's in, possibly it's a greater than or equal to, possibly it's a less than or equal to, possibly it's an equal to constraint. We have to look at each one by one and address each one separately. Let's just keep in mind that our goal is that we want the left-hand side to be smaller than the right-hand side after multiplication with the dual variables. So once we take the linear combination, we want the right-hand side, which will end up being the dual objective function, that to be larger than the left-hand side, which itself is in turn larger than the primal objective function. So, all right, so how do we make that happen? So we multiply each of the constraints by a dual variable. So 3 constraints, 3 dual variables. And so since we want, after multiplication, for the left-hand side to be smaller than the right-hand side, see, for this first constraint, this is a greater than or equal to constraint. And so what we need is for y1, we need to impose a particular constraint on it then. y1 needs to be less than or equal to 0. That way, after you multiply by a non-positive number, that'll flip the direction of this inequality, and this greater than or equal to will turn into a less than or equal to after multiplication with y1 on both sides. And that way the left-hand side really will be less than or equal to the right-hand side, which is what we want. Okay, and so by similar reasoning, we have a less than or equal to for the second constraint, so the second dual variable, y2, should be greater than or equal to 0. That way, when you multiply by y2, that'll preserve the direction of this inequality, which is what we want. We want a less than or equal to here. And then finally, we have an equals to for the final constraint. So it actually doesn't matter what y3 is. When you multiply by y3, independent of what it is, you'll still have an equality. So y3 is free. And so the left-hand side, after multiplication, will be less than or equal to the right-hand side, because in particular, it will be equal to the right-hand side. Okay, so looking one by one at the primal matrix constraints, we were able to one by one construct the constraints for the dual variables as well. So for each constraint, there's a dual variable, and you have to do them one at a time. And so this establishes that y transpose AX is less than or equal to y transpose B. And that fact is true by the constraints on these dual variables that we just imposed. But there's another thing that we need now. We need that y transpose ax is greater than or equal to c transpose x. So we need to show that that left inequality is also true. So how do we consider that to be true? Well, view this as being a vector c transpose and a vector y transpose a. Those are the vectors, and they're each being multiplied by x, dot product with x, basically. Well, x comes with 3 components, and we have no control over what those components are. They're pre-specified, but they're not necessarily of any uniform type, so we have to, again, look at each component individually. So correspondingly, we're going to look at each of the components of C transpose and Y transpose A individually as well. So, so let's look at C1 and Y transpose A 1. And I guess technically it should be C1 transpose, but they're just numbers after all, so whether it's transposed or not really makes no difference. But anyways, C1 and Y transpose A1, these are the first components of the respective vectors C and Y transpose A. These are going to be multiplied by x1. So x1 will multiply C1 and Y transpose A1, and we know that x1 is greater than or equal to 0. And that comes from the formulation of the primal linear program. And so since this is greater than or equal to 0, and at the end what we want is for the part with C to be less than or equal to the part with Y transpose A after multiplying by the x component, so we want a less than or equal to, so then originally we should also have a less than or equal to before multiplying by x. Because after we multiply by a non-negative x, that will preserve the direction of whatever inequality we place here. So we should place the inequality that we want at the end as well. So we want a less than or equal to at the end, so we should place a less than or equal to at the start as well, because x1 is greater than or equal to 0. And so that reasoning applies for the next 2 components as well. So C2 transpose and Y transpose A 2. And now x2 is free. And so since x2 is free, that means we need an equality constraint for this second component of C and Y transpose A. So they're going to be multiplied by x2, which is free. And see, if we did anything else, if we did a greater than or equal to or a less than or equal to, what would happen is that since x2 is free, it can be positive or negative, and it could flip the inequality direction at a moment's notice, and we wouldn't have the less than or equal to that we want. So we need a stronger constraint, which is equality, so the left-hand side will be less than or equal to the right-hand side, because it'll be exactly equal to the right-hand side before and after multiplication by x. Finally, we have C3 transpose and Y transpose A3. And these will be multiplied by x3, and x3 is greater than or equal to 0. And so that means we should impose that C3 is less than or equal to Y transpose A3. So with all those constraints, these will be the matrix constraints, and up in the top right here, these are the dual variable constraints. Those are all the constraints that we need to impose in order to show that both of these inequalities that come from here are true, and then that establishes that weak duality is true. And so we can now write down the dual linear program. We're minimizing the upper bound B transpose Y, and it really will be an upper bound once we impose these constraints. So so we'll have A transpose Y. So A transpose Y is the same thing as Y transpose A. We've just transposed it now. So it's a column vector, whereas Y transpose A was a row vector. Okay, so A transpose Y, the first component should be greater than or equal to C1. Second component should be equal to C2. And the third component should be greater than or equal to C3. So the right-hand side there, that's a vector as well, with components C1, 2, and 3. And then we need the dual variable constraints. So we need y1 less than or equal to 0, y2 greater than or equal to 0, and y3 is free. And that is the formulation of the dual linear program. And so, again, we had to do each of these constraints one by one because there could have been different types of constraints that appeared in the primal, and indeed there were different types of constraints. So we couldn't assume that all the constraints would be of the same type, and so we also couldn't assume that all the dual constraints would be of the same type either. So everything was just done individually. Okay, and here is the same linear program. It's just cleaned up now. So if I just get most of it in view, you can just see. So here we have B transpose Y. We just filled in what the data B is. It's -2, 2, 13. The C component data got filled in, 12, 26, 20. And the matrix A became transposed, and that's it right here. And then all the constraints are in the appropriate directions. So it's just cleaned up now. Okay, and so now let's do a comparison. So we have these two linear programs. Here on the left is the primal that we started with, and here on the right is the dual that we just obtained. But if you remember from the prior video, what we obtained as the dual was not this thing on the right. However, it certainly seems like this should be the correct thing, because these primal matrix constraints corresponded to these dual variable constraints, and these primal variable constraints corresponded to these dual matrix constraints. And we on an individual basis. So x1 corresponded to the first matrix constraint, x2 corresponded to the second matrix constraint, etc. So it seems like that should have been the right thing, but they don't look like the same linear program. What was the linear program from before? Well, here's what we have now. This is the linear program that the dual that we just derived, and here's what it was before in that prior video. So what happened before is we had everything of a uniform type, and then we took the dual, and again, all the constraints were of a uniform type, all matrix equality constraints and all variable non-negativity constraints. So it looks like they're different linear programs, at least at the surface level. But in fact, as this comment over here says, these linear programs actually are the same linear program. So that'll be something that we'll address in the future. I don't want to address it right now simply because it's not the purpose of this video. And right now we're trying to simply show how to construct the dual directly rather than doing this conversion. We're not so I don't want to get sidetracked with showing that these two things are equal, so I'll make a follow-up video showing that they are equal. But they are in fact equal, and it shouldn't be overwhelmingly surprising because we have a -2, 2, 13 is the coefficient data up top, and then on bottom it's 2, 2, 13, -13, 0, 0. So there's 2's and 13's involved, and so it looks like they could be the same, or it's believable at least, and in fact they are. So what we've done really does correctly construct the dual linear program. Okay, so with that in mind, we can now mechanically take the dual from now on, in the sense that we used our logical reasoning to decide what the appropriate constraints should be, but now we can simply replace our reasoning with just mechanical rules that we can just program into a computer algorithm, and it can just do it automatically every single time for us. And we know the reasoning behind it, but we don't have to think about it each time. We can just mechanically do it. So if we started with a maximization problem and we took the dual, it would be a minimization problem, and a less than or equal to matrix constraint that appeared in the primal maximization problem. Correspondingly, there would be a dual variable, and that dual variable would be a non-negative dual variable. Or if we had a equality constraint in the primal, then the corresponding dual variable would be free, etc. So you can just read down the list, the left and the right correspond, and in fact it goes the other way around as well. So if we started with the minimization problem as our primal, and we took the dual, and we would get a maximization problem, then say we had a greater than or equal to constraint for the minimization problem, then we would have a greater than or equal to 0, a non-negative dual variable, etc. So the variables of the dual of the primal would correspond to matrix constraints of the dual. So we would get this. These constraints would correspond to these variables, and these variables would correspond to these constraints. From the left to right. So that's the rule. Those collectively are all the rules for how to take the dual of individual constraints, and so now we don't need to have them all be of the same type. We can deal with them on a case-by-case basis. And the reason that these rules are what they are, remember, is the purpose is to ensure that weak duality holds, which is what we always want. So weak duality being that if we start with C transpose X and we're trying to maximize it, then the dual should be B transpose Y, and we're trying to minimize it, and we should have that B transpose Y is greater than or equal to C transpose X. Or if instead we started with B transpose Y, then the dual would be C transpose X, and it would be a lower bound on B transpose Y. But anyway, so this inequality is effectively what weak duality is saying. We want this to be true, and it will be true, provided that you impose the appropriate dual constraints, which is what we do. Okay, so we can consider duality now in total generality. So we don't have to have anything be of a uniform type anymore. We can have all sorts of different constraints. So here is a linear program which we took it to be a maximization problem, and so there's just all sorts of constraints. There's basically 6 types of constraints: 3 matrix types of constraints and 3 variable type of constraints. So up here we have the matrix constraints that can appear. So we have a row of the matrix times x being less than or equal to the right-hand side component. So we'd have a less than or equal to matrix constraint. We could have an equality matrix constraint or a greater than or equal to matrix constraint. And so we could have as many of those as we want, and those would be indexed for I in M1, M2, and M3. So type M1 is the ones that are less than or equal to, type M2 are the ones that are equal to, and type M3 are the type that are greater than or equal to. And then similarly for the variables as well. So we have 3 types of variable constraints that could appear as well. Variables can be non-negative, free, or non-positive. And so those would be, for those components, they'd be indexed by types N1, N2, and N3, corresponding to these 3 possibilities here. And then in the dual, what happens is that these matrix constraints of the primal correspond to the dual variable constraints. And you can see that type M1 here, so that's a less than or equal to constraint, that'll give us a non-negative dual variable constraint. So that's for types M1. And for type M2, equality constraints gives us y, that component of y being free for types of M2, and so forth. So you get the idea. And then same thing for the primal variables will correspond to these matrix constraints up top. So we have types N1, 2, and 3, and again, types N1, 2, and 3 up top here. Just one thing on the, one remark on the notation here. Why are all these transposes showing up? Well, it's rho J, A transpose, transpose Y. Well, okay, the interior transpose is there because when you take the dual, the matrix A becomes transposed. So that's why that interior transpose is there. And then the outer transpose, that's the one that signifies we're taking the dot product of 2 vectors. So we're taking the dot product of the vector of the jth row vector of A transpose with Y. And then that's a number which is greater than or equal to Cj for that first type there. So that's why there's 2 transposes. And note that row J of A transpose, so a row of A transpose is a column of the original matrix A. So we could have written this as, so this constraint could have been AJ transpose Y greater than or equal to Cj for all J in N1, where AJ is the jth column of the matrix A, and then that dot producted with Y. But I just wrote it like this so that it would be of the same format as the primal objective function, primal matrix constraint as well. And then same thing for the next 2. We could have had AJ transpose Y equals CJ for the J's in N2, and AJ transpose Y is less than or equal to CJ. Is less than or equal to Cj for types of J in type N3. Okay, so let's just go through weak duality in this most general case now. So that is, if x is feasible for the primal and y is feasible for the dual, then we want to show that C transpose X is less than or equal to B transpose Y. That's the fact that we want. And it's true once we impose these particular constraints. And so the fact that we have imposed the constraints means that weak duality is true. So let me just show you how it all ends up working out. So this will conclude the video. Basically, we will see that now that we can take the dual directly, independent of what type of constraints appear in the primal, we know the corresponding constraints of the dual, and weak duality holds. That's what we wanted. So that will conclude the video. So C transpose X, okay, that we can write that as CJXJ. And we sum over all indices J. So that's just what C transpose X is by definition, basically. But we can break those components up. So instead of summing over all the indices J all at once, we can do it type by type. So there's 3 types of components Xj. There's the ones that are of type N1, 2, and 3, respectively. So we can break this up. We can sum over the J's in N1 of CJXJ plus the J's in N2 of CJXJ and plus the J's in N3 of CJXJ. And once we write it like that, now we can use what it means to be of type N1, 2, and 3, respectively, to in order to establish bounds. So CJXJ for J's in N1, XJ is non-negative for J's in N1, as we can see in the primal constraint here. And then correspondingly, the dual constraint is that rho J of A transpose that multiplied by Y, or in other words, AJ transpose Y, is greater than or equal to CJ for J's of type N1. So CJ is smaller than AJ transpose Y, and XJ is non-negative. So then this first part is smaller than AJ transpose Y times XJ. And that's for the J's in N1. And we can do similar reasoning for the next 2 parts. So for the J's that are of type N2, XJ was free, but then CJ equaled the left-hand side, which was AJ transpose Y. So this equals, so for J's in N2, this equals AJ transpose Y XJ. And then finally, for the third part, here the XJs are less than or equal to 0, but correspondingly the CJs are smaller than the, they're larger. You can see here, for type N3 here, the CJs are larger than the AJ transpose times Y. So those 2 facts combined, so CJs are bigger, but the XJs are negative. So then overall, when we take the product, that'll be less than or equal to the sum of the J's in N3 of AJ transpose Y times XJ. So so then when we sum everything together, we can, and there's each of these things up top is upper bounded by the thing on bottom. So we sum everything on top together, we can sum everything on bottom together, and then the overall thing on top is less than or equal to the thing on bottom here. And what is this thing on bottom? Well, you can just imagine doing the algebra. AJ transpose Y is the same thing as Y transpose AJ. And then there's a Y transpose in front of everything, so we can factor the Y transpose out of the entire summation of all of these terms. And then we're left with AJ times XJ, and it's for all the J's in N1, 2, and 3, so it's just summing over all AJ XJ's overall, but that's exactly what the product A times X is, the matrix A times the vector X. So anyways, you can work it out more carefully for yourself if you'd like, but this turns out to be Y transpose AX. So that's the algebra that would happen there. And so what we've just shown is that C transpose X is less than or equal to Y transpose AX. And so that's the first part that we needed, and now we can rewrite Y transpose AX and show that it's smaller than B transpose Y. And it's very similar to what we just did. So Y transpose AX, that can be rewritten as, we can write this as, we'll sum over the indices I now. So this will be yi rho I of A transpose X. So imagine taking a row of the matrix A and multiplying by the vector X. And so, and you do that for all the rows, and that's going to give you a, for any particular row you do that, that's going to give you a number, and that number gets multiplied by yi. So anyways, this is the dot product of y with ax. Okay, so imagine doing a times x first, and then taking the dot product with y transpose, and this is what it is on bottom. Okay, and the reason to write it like that now is now we can go over the indices I. So this will be equal to maybe I should write it here. This will be equal to the sorry, never mind. I'm going to go back down below. This will be equal to the i's in type M1 of yi rho I of A transpose X. And then we do types M2 of yi rho I of A transpose X. And then finally, the i's in M3 yi rho I of A transpose X. Okay, and so these are all the parts. So we've summed over all the separate parts separately now, and then we just use what it means for each of these indices to be of the particular type. So to be of type M1, for instance, that means if we go up top here, type M1, that was where rho I of A transpose X was less than or equal to bi. And it was also the part where the corresponding dual variable yi was greater than or equal to 0. So then overall, if you combine those two things, this first part right here has an upper bound of, we can just replace this with yi times bi, because bi is larger than rho I of A transpose X. So this is for the i's in M1. And then similarly for the i's in M2, that's where rho I of A transpose X equals bi, and the yi's were free there. So this equals i's in M2 of yi bi. And then finally for the last part, this is where the rho I of A transpose X that was it was larger than the bi component, but then the yi's were negative. They were less than or equal to 0. So the multiplication of a negative thing with something that was larger than bi makes the overall thing less than this on bottom, less than yi bi. So the rho I of A transpose X was larger, but then the inequality gets flipped because the yi is less than or equal to 0. So this is for type M3 here. Okay, and so now you can just see that now that we've established this upper bound is true, it's true because of the constraints that we imposed, and now we're just, this is the sum over all the parts. So parts M1, 2, and 3, and so that's just everything. So this is equal to the sum of all the i's of yi bi, which is the dot product. That's y transpose b, or in other words, b transpose y. And so there we have it, because, so I should have said now we're summing on bottom here. This was a sum here. So this overall thing on top was less than or equal to this overall sum on bottom. And that overall sum on bottom works out to be exactly b transpose y. So then what we've just shown is that c transpose x right here is less than or equal to, less than or equal to, less than or equal to, keep going down, all the way until you get to less than or equal to b transpose y. And so therefore c transpose x less than or equal to b transpose y, which is what we wanted to show. So weak duality does hold, and it's not by any coincidence. It's holding exactly because of the fact that we imposed the appropriate dual constraints, and that's what makes it work. Okay, so in summary, what have we done? Well, now we know how to take the dual of a linear program even when it is not of a uniform format, and weak duality will hold as well, which is what we wanted. So no matter what the constraints they throw at you are, you can take the dual of a linear program as posed now. The only thing that's left to do is to show that the linear programs from the initial example that we had are actually the same linear program. So that will be addressed in the follow-up video to this, where we conclude everything from here. So that's it for this video. Thank you for watching.